All right, now we want to talk about circular orbits. Now, a while ago, we talked about projectile motion, right? When I threw the tennis ball around the room or whatever I did. And when we talked about just projectile motion, we assumed flat Earth, right? Flat Earth. And that's fine, when your projectile is not going very far, But now we're talking about orbits. So obviously you can't talk about a flat Earth anymore. So now we're going to assume we have a perfectly spherical Earth, which is not correct either, right? But it's a good assumption, all right? It's a good assumption. Okay, so here's the question. The question is, so just pretend, the last time we saw this slide, I think I said something, I'm throwing a ball, right? Well, now we're going to say we have a communications satellite in orbit, okay? So why doesn't a communications satellite crash into the Earth? So what's the answer to that question? It has the right speed, remember? This would be too slow, B would be too slow, C would be too slow, D has just the right speed. So it goes completely around the Earth, right? Completely around the Earth, okay? All right, so let's say you're hired by a satellite company to figure out the speed. How would you do it? It's actually a piece of cake, believe it or not. Okay, so let's say that the satellite is close enough to the Earth that for the force of gravity, we can just use the weight, mg. So we don't have to use Newton's law of gravity, okay? All right, so we have a satellite orbiting the Earth. So circular motion. So what do we write down? Without even thinking, we just write it down. Sum of the radial forces equals mv squared over r. Now, why did they say mv squared over r and not mr omega squared? Well, because we want to know the velocity, right? I mean, we could have, they could have asked us for omega, but they didn't. Okay, so that's always right. It's always correct. Write it down. Okay, now, how many radial forces are there? One. What is it? Gravity. And again, I said that we're close enough to the Earth, we can just use the weight. Well, what's the equation for the weight? mg, right? There you go. Okay, so we want to solve for the velocity. So we just look at this, right? So I can erase that. What do you notice? What cancels? The mass. Well, surprise, surprise, right? So mass cancels. Multiply both sides by r. Take the square root. Bingo. Okay. All right, so that would be that. This is the speed that's required to put a satellite in orbit if it's close to the Earth. And again, it doesn't depend on the mass. So if we had no air resistance and we had a perfectly spherical Earth, you could put a car, right, as a satellite. You could put a comb, a plastic comb for a satellite. You could put a ping pong ball, whatever, as long as we're ignoring air resistance. This would work for anything because it doesn't depend on the mass. All right. Okay, new topic. Remember this? So this is an old slide. Let's just go over it. You are a passenger in a car not wearing your seat belt. Without increasing or decreasing its speed, the car makes a sharp left-hand turn, and you find yourself colliding with a right-hand door. Which is the correct analysis of the situation? And I pointed out, correct means a perspective of an inertial reference frame. Remember, inertial reference frame means the acceleration is 0. So when you're going in a circle, when you're making a turn, you are not an inertial reference frame. What would be an inertial reference frame? Well, let's assume there's a drone, right? A drone is just being stationary, and it's watching this whole thing, okay? So what's the correct analysis? Starting at the time of the collision, the door exerts a leftward force on you, right? Remember that picture? So, you would go straight unless there's an external force acting on you. If you're going left, there has to be something pushing you towards the center of the circle, right? So the door provides the center-directed force, the radial force, that makes you move in a circle, okay? All right, so we talked about that a long time ago, right? I mean, but how do you feel? You know, you're the passenger, you know? You feel like you're being thrown to the right, but that's because you're in a non-inertial reference frame, so we don't care about it because we only deal with inertial reference frames. Okay, so, but wait a minute. I mean, you know, I really feel like I'm being thrown to the right. And I know that's, you know, not inertial and all that, but I feel it. But we don't care. So, because we can't use Newton's laws on it. So we're going to call what you feel, you know, as a passenger in a car, we're going to call that a fictitious force. And we're never going to mention it again, all right? We're just not going to deal with it, okay? So it's the bottom line. If you want to use Newton's laws, you've got to work in inertial reference frames. End of discussion, okay? Well, not totally end. Now, but hold it. Is Earth really an inertial reference frame? No. I mean, it's spinning, right? Then it's orbiting the sun, and then our solar system is orbiting the galaxy, and that's orbiting something else, right? So it's not. It's not an inertial reference frame. But is it almost an inertial reference frame? Yeah. So it's close enough, so we're going to just assume that the Earth is an inertial reference frame. And the book has a very short, nice description of you know, it's not, and because it's not, here are some results, okay, or observations, okay? So you ought to just read that in the book. It's kind of interesting. Okay, here's a really nice question. A rider in a barrel of fun finds herself stuck with her back to the wall. So what, I don't know, they actually have these crazy things. So you stand, so there's a cylinder, right? And you stand and your back is touching the wall of the cylinder. And there's a floor. And then they raise you up, you know, the whole cylinder moves up high, and then you start spinning it. And when it's at a certain speed, the floor drops out, so you can actually see the ground below you. And you don't fall, you don't slide down, okay? All right, so a rider in a barrel of fun finds herself stuck with her back to the wall. Which diagram correctly shows the forces acting on her? Now remember, what did we just learn? Always work in inertial reference frames. Is she in an inertial reference frame? Absolutely not. She's going in a circle. So you got to pretend there's a drone or something, or a hummingbird stationary just looking at all this stuff. So this is an incredibly important question. So please do it. Don't just look at my answer. All right, so pause your video and figure it out. All right, so look, there has to be okay, there's weight, right? There's weight. Now, there has to be friction, right? I mean, if there were not friction, she would slide down. So there has to be friction, and what's the direction of friction? It's opposite the direction of motion, right? And so if she slid down, she'd just go zoop. So friction has to be zoop, you know? Okay, so friction has to be vertically up. Now, she's going in a circle, so there has to be a force towards the center of the circle. So what's the only one that works? Yeah, that one, right? I mean, this is crazy. You know, I mean, first of all, there's no friction. Second of all, what in the world is that? That's not towards the center of the circle. Okay, here, this is great, but there's no friction. Here, that's good. What in the world is that? I mean, the friction goes like, you know, opposite direction of motion, right? And here, this is nuts because this points away from the center of the circle. So here, friction, because, you know, again, she would slide down this way because of the weight. So friction is opposite direction of motion, and this points towards the center of the circle, which is what we've been talking about for the last 50 minutes, right? Okay. All right, now we're going to do this awesome problem. And I did not write this. This is an awesome problem. Oh, gosh. So here, it's the same, they have these things in amusement parks. So here they call it a barrel of fun, and here they call it a rotor, okay? All right. Even some seasoned roller coaster riders blanch at the thought of riding the rotor, which is essentially a large hollow cylinder that is rotated rapidly around its central axis. Before the ride begins, a rider enters the cylinder through a door on the side and stands on a floor up against a canvas-covered wall. The door is closed, and as the cylinder begins to turn, the rider, wall, and floor move in unison. When the rider's speed reaches some predetermined value, the floor abruptly and alarmingly falls away. The rider does not fall with it, but instead is pinned to the wall while the cylinder rotates, as if an unseen and somewhat unfriendly agent is pressing the body to the wall. Later, the floor is eased back to the rider's feet. The cylinder slows, and the rider sinks a few centimeters to regain footing on the floor. Some riders consider this to be fun. All right, so suppose that the coefficient of static friction between the rider's clothing and the canvas, on the wall is 0.4, and the cylinder's radius r is 2.1 meters. What minimum speed v must the cylinder and the rider have if the rider is not to fall when the floor drops? Okay, so again, you find these things in amusement parks, and somebody has had to do this calculation, right? Because you don't want people to fall and die, correct? So anyway, let's do it. Now look. All right, let's just do it. Stop talking. Okay, let's see. Okay, so we have the force diagram was drawn. We discussed it, right? That was the last. It was this, right? This is the force diagram. Friction, weight, and what's this? It's the normal force, right? It's the normal force pointing towards the center of the circle. Okay, so here's the force diagram. Friction, weight, normal force. Okay, so the sum of the radial forces, and we want to know V, right? So sum of the radial forces equals mv squared over r. Okay, as I say a million times, this is true, so you write it down. But now we got to figure out, we got to write down what is the radial force. There's only one radial force, and it's the normal. Okay, so it's the normal force. Okay. So there you go, right? All right, so we want to solve for the velocity. So goodbye. Solve for v. Multiply by r, divide by m, square root. There you go. Okay, are we done? I mean, this is true, but are we done? No, we are not done. How come? Well, because I don't know what the normal force is, right? I don't know what the normal force is, okay? Oh, man. Okay, so what am I going to do? Well, we started off, I did it differently this time, right? Usually I do the z problem and then the r problem. I just did it differently just for fun. Okay, so we did our r problem. We realized we don't have enough information. So now we're going to do the z problem. Okay. So the sum of the z forces. Now remember, this poor woman is stationary, right? So she's not accelerating up or down. So the sum of the z forces, we have Fs max, right? It's max because we want to know the minimum speed. So we have Fs max up minus mg down. That equals 0. Agree? Okay. Now, Fs max. Okay, so this here. So we have. So that says that Fs max equals mg. But what's Fs max? Fs max is mu s n, right? So we have mu s n equals mg, right? Equals mg. So I wanted my n up here, so the n is just mg over mu s. Okay. So now I'm going to plug that n up here. So I have square root. So n is mg over mu s. That's the n. Then I have an r. Then I have an m on the bottom. Okay, so what happens with the m? Oh, I got to make this r uppercase r, right? Sorry. Uppercase r, right? That's what they use in the problem, uppercase r. What happens to the m's? They cancel. Wow! Surprise, surprise, right? M's cancel. So that's the answer, okay? So the answer is gr over mu s. Let's get a number just for fun. So g, 9.8 meters per second squared. Okay, what's the radius of this thing? 2.1 meters. 2.1 meters. And what's mu s? 0.4. That equals 7.2 meters per second. Okay, there you go. Now, what do you notice? I've already said it, independent of mass. So in other words, you know, if this were at an amusement park, you don't have to sit, there's not going to be a sign, you know, you have to have a mass greater than whatever or a mass less than whatever in order to ride this thing. Independent of mass, okay? Independent of mass. And again, when you're in this thing, like I said, you feel like you're being pinned to the wall, right? Well, again, that's that fictitious force because it's in a non-inertial reference frame. Okay? Now, what else? Notice that the static friction, okay, so static friction, you know, okay, so static friction equals mu Sn, right? No kidding. So the frictional force, which is the important thing, right? I mean, you got to have enough frictional force, unless the lady's going to die and, fall and die, right? Okay. So the frictional force depends on the normal force. Agree? I mean, it's right there. But, right? But also, I erased it. But also, look, we have the sum of the radial forces equals mv squared over r, which was n, right? Okay, so the friction depends on the normal. But look, the normal depends on the velocity squared, right? Squared, okay? So obviously, the larger the velocity, the larger the normal force, larger the normal force, larger the friction. Which means, okay, so, all right. That's what we want, right? We want it to be enough friction so the person doesn't slide down, okay? So there's kind of a nice little problem. Okay, now, I keep writing the sum of the radial forces, but we've only had one radial force in the problem so far. So you might think, what a waste of time to write that. Well, let's do a problem where there's more than one radial force. Okay, so here's a car traveling at V and goes in a valley. Now, we want to use what we're learning, right? So we're going to assume that this is a perfectly circular valley, and this is a perfectly circular hill. Okay? It's all right. It's approximately true, you know? So, how are we going to do it? So let's do B here. Okay, now notice, this is the center of the circle, right? So what are the forces acting on the car? There's the normal force, and there's the weight. But this is the circle center, so the normal force points towards the circular center, towards the center. So remember, don't even think, just write it down. Sum of the radial forces equals mv squared over r. But now, you're going to write what the radial forces are. Okay, so there's a normal force, which is a plus, because it points towards the center of the circle. And there's the weight, which points away from the center of the circle, so it gets a minus. Okay, so that would be how you do that. All right, that's how you do it. Okay, let's do C. Okay, again, just write it down. Okay, now this one's different, because now this is the center of the circle, so the weight points towards the center, The normal force points away from the center. So now we're going to have mg minus n, right? The weight points towards the center, so it's positive. The normal points away from the center, so it's negative. So there you go. Make sure you understand this. All right, let's quit.